So the key part to taking our inverse Laplace transform is being able to do partial fraction expansion. So over the next several videos, we're going to be focusing on how to do this. So let's start by considering this proper rational function, f of s equals s plus 6 divided by s times a quantity s plus 3 times a quantity s plus 1. So of course we could rewrite this and sort of break up the denominator into the different poles. So could rewrite as f of s is equal to, we could say it's something over s, let's just call this constant k1, plus something over s plus 3, and let's give this another, name this another constant k2, plus something over s plus 1, and so let's say this is constant k3. So if we ignore for the moment that we don't know the values of k1, k2, or k3, we can say that we know they're just going to be some constant value. What we could do is we could easily look at a table of Laplace transform pairs and inverse transform this. So table of LT pairs, and again we want to keep in mind not just pairs but also our operational transforms. So operational transforms as well as functional transforms. And so what we could see is doing that, we could say our inverse Laplace transform, so inverse Laplace transform of our function f of s is equal to f of t, and in this case we would have k1 plus k2 e to the minus 3t plus k3 e to the minus t, and all of that multiplied by our unit step function u of t. So basically all we need to do is figure out the value of these constant terms k1, k2, and k3, and then we could fully specify what this function is in the time domain. So let's just say we only need to find, so clean that up a little bit, so we only need to find our values of our constants k1, k2, and k3. So once we know these three constants or these three coefficients as we see them in our time domain equation, we know the answer to our inverse Laplace transform. So in general, we're going to have four cases. So in general, we have four cases depending on the format of our denominator. So depending on our denominator polynomial, which I'm just going to write as d of s. So recall before what we had said is our f of s in general can be characterized as some numerator polynomial divided by some denominator polynomial. And so based on the form of this denominator polynomial, we have four different cases. So what those four cases are is we can have one, real and distinct poles. And so this is the case that we see above. And so as we've talked about before in a different unit, essentially our poles of this function, f of s, are just going to be values of s that make our function equal to zero, or make our denominator equal to 0, which make our function go to infinity. And so in this case, we see that our poles would be 0, -3, and -1. So in this case above, we have case 1. The second case is we could have real and repeated poles. And so we'll come back to that in a later video and look at exactly how to deal with that, but as the name implies, that's just essentially if we have a case where we have more than one pole at a specific location. So maybe we have two poles at s equals -3, for instance. The third case is if we have complex and distinct poles. And so the only difference here is it's similar to case 1, but we're just adding complex numbers into the mix. And then, as you might be able to guess, our fourth case is going to be complex and repeated poles. And so we're actually not going to cover this in detail, this fourth case. So let me just put here that we won't consider this. But basically we could easily extend this idea. It's going to be the same as case 2. We're just going to be dealing with more complex math. So what we're going to do over the next several videos is we're going to spend time looking at each of these, well, not each of these 4 cases. We're going to look at the first 3 cases, and we're going to come up with a generalized equation that we can use for each case, as well as look at some examples of each case.